像呢 Okay, great. Hello everyone. So welcome to the weekly seminar. So today it's a great honor to have Professor Eric Xing, Professor CMU and the President of Mohammed bin Zayed University of Artificial Intelligence and founder and chairman of Patun, the AI company. So Eric is a very well-known researcher and entrepreneur. And so there's no need for me to give a very detailed introduction. So I would just let Eric to start the presentation. So Eric, please start your presentation and welcome to Baidu. Thank you.
Oh, thank you very much, Ping, for the very generous introduction. And good afternoon, good morning, good evening, everyone, depending on where your time zone is. Here I have, I'm in my early morning time right now. Right, so today I'm going to give a talk about some of the work I've been doing in the past several months. In fact, during the pandemic, I guess things slowed down quite a bit, and it's actually a good time to do some housekeeping and to do some adventure. So what I'm going to present today is a result of such a major housekeeping kind of activity on my research. I'm trying to summarize and integrate many of the work happened in my group, into a more overarching picture. And also under that umbrella, we did some adventurous thing, to push the envelope a little bit. So I'm giving a big title to address issues in learning, in meta learning, and also to have a perspective of the way what I call the Lego learning, which is a particular way of implementing ideas in learning and meta learning. Before I start, I want to make sure that I mention the name of a few key contributors. So these are the key contributors of the content presented in today's talk. They are my current and former students in the group, who are now everywhere. As you can see, they are faculty and postdoc and business leaders in different organizations. I'm not going to read their names, but if you want to collaborate with them, you won't go wrong. They were really brilliant, and in fact, the ideas and the results I present today are all coming from their hard work. All right,
Eric, maybe could you try to get rid of the next slide, or maybe maximize the screen?
Get rid of what slide?
Oh, there's next slideshow. Maybe you can just, I don't know how you do it, but maybe only maximize the current screen.
So you're in the presenter mode.
Oh, I'm in the different red mode. Oh, I see.
Yeah, it's presenter.
I didn't realize that. Let me try. So you are seeing the presenter mode, not the bigger mode.
No.
Let me give a second. Okay, so give me a second. Is this the right mode?
No, not yet.
Still not my right mode. Okay. Let me give another try.
Very good. Thank you.
It is right mode right now?
Very good.
Hello? Ping, can you see me? Can you hear me?
Yeah, this is good. Thank you.
This is the right mode?
Yeah, it is.
Okay. Let me also, do you hear my audio okay? Everything's okay, right?
Yeah, it's good.
Okay, good. So sorry for the glitch. Let me start the actual technical work. So as we can see, right now there is a huge enthusiasm, in machine learning over developing, benchmark and the leaderboard-driven results, right? And to the point that there are a lot of effort in developing, major models, to catch high scores and reach high marks, in those leaderboards. And we see a dramatic growth of model sizes, in particular in NLP and the CV applications. So it looks like there is an arm race, of computing power and the money, to push forward machine learning and AI. But when we turn to real-world applications, we sometimes see a very different, scenario. For example, here I show you an example of the healthcare applications. Right, you can see that they are very complicated, use cases where you have all sorts of data, such as the clinical notes, such as radiology pictures, genomic data, and so forth. And for a typical healthcare application, the model or the solution we provide needs to be able to integrate this kind of data and also come up with a complex output, not just a kind of a benchmark classification or tagging accuracy, but very often time, complex content generation, such as report, such as narratives, and also they need to be explainable. So that's obviously pushing the boundary of what the heavy parameterized big model is able to provide. Among all these different topics, one of the major technical problems, on the theory and the modeling side is to how to deal with, data and experience of all kinds. So here I repeat what I just showed in the medical domain. We have for those who are not speaking, can you mute your camera, mute your speakers?
I'll let them know. Sorry. Okay.
All right, thank you very much. Yeah, we are having all these different data and experiences of all kinds, right? So you have typical examples which are either labeled or not labeled. And then in a real world scenario, you very often get rules and constraints provided by domain experts. You may have structured knowledge such as a knowledge graph. And then if your learning scenario allows you to interact with the environment, you get rewards, auxiliary experiences from the agents or adversarial experiences from a challenger. And sometimes you may have a chance to work with a master, for example, that you can imitate from. So all these experiences right now are handled by very specific models. Right? So we have this marketplace of algorithms and heuristics, each of which are customized, specialized for a particular type of data or experience and a particular type of learning paradigm, such as like reinforcement learning, adversarial learning, transfer learning, and so forth. And then when we talk about deployments or maybe training on large data using large model, you oftentimes need to also deal with the system problem, using different back-end configurations or structures and so forth. So this is a very big space for any solution provider to master, to navigate, and also to pick solutions from. So back to, for example, this healthcare application. Suppose we want to, provide a solution to do the medical case report generation, like what I showed here. You are given a radiological picture, and you automatically write, a clinical case report. The amount of work involved is pretty broad and also hard to manage. It involves, both, data processing, model and algorithm development, and also system and infra development. So it's really, really, a very, overwhelming amount of labor. And the effort needed, in completing this kind of work, can be present at all levels. And here I just want to give you, a snapshot about how this different work, can be categorized. Because our goal, is to provide a little bit more clean and, principled approach to better the effort at each level. Hopefully, based on a more predictive and principled approach. That's what I mean by, doing the house cleaning of many of our earlier results and to integrate them with a more kind of clean mathematical framework. We need to, first of all, build and compose complex models. and hopefully unify a number of different paradigms so that they can be integrated. We need to then pipeline, all the parts, at different stages of the solution so that they can integrate into a system. Is there a way to mute all the speakers or all the attendees? Thank you.
There's someone monitor this very closely, so yeah.
Okay.
Yeah.
And then with all these components, we also need to tune those hyperparameters, and also even do maybe architecture search to optimize the learning vehicle itself. And then for large case training and the inference, we need to sometimes do distributed inference into parallelize all the job. And then if you have multiple jobs running on the same computing infrastructure, then we need to do scheduling. So I think all this needs to be optimized when we are talking about an industrialized solution. And someone need to basically take care of this, in my opinion, from a holistic view to make sure that the optimization is universal and it is generalizable. So with that, I'm going to present a collection of results leading to model-based optimization through all the steps of a machine learning operation. And we want to show a roadmap toward principled and more predictable production level AI. Right? So with that, today I'm going to discuss 3 major results in which we achieved in the past several months. One is on how to learn using a more standardized approach, then how to meta learn, using also a standardized and model-based approach, and finally how to Lego learn using a set of tools. To begin with, let's look into the problem of learning. As we all know, machine learning over the past several decades has evolved into a pretty mathematically heavy field with equations and principles of all kinds. And that's why we have a marketplace of heuristics and algorithms. And in fact, if we look into some other fields, such as physics, in the past several decades, if not multiple hundreds of years of evolution of the field of the physics, there has been at some point explosion of the number of formalisms and equations to describe all the physical phenomena. But then there are efforts toward reduction of this equation to use what sometimes is known as the standard equations or standard models to unify many seemingly different learning paradigms of physical phenomena, such as through the Maxwell equation, electricity and magnetism become unified, and through the Mills and the Young standard model, now weak force, strong force, electromagnetism, are also unified, except the gravitational force. So obviously, this is intellectually very interesting because it brings both, the simplicity and beauty, of the basic foundation of this phenomenon, but also it makes, application work, production and industrialization also, more explicit and easy, such as, the coming of the electronics age and so forth. So in machine learning, we've spent some time, in my group, looked into, all the well-practiced mathematical framework of machine learning, such as the maths behind maximum likelihood supervised learning, unsupervised learning, Bayesian inference, posterior regularization, and so forth. And we found that there may be a possibility of also introducing a standard model-like equation, like what I present here, to subsume all of the existing learning paradigms. So this is what this standard equation look like. It consists of 3 terms. The first term is what I would like to call experience function, which can be used to encode data examples, rules such as the regularizers in posterior regularization, rewards such as the rewards you see in reinforcement learning, by instantiating different mathematical form of this f function. The second term is called a divergence function. It is used to minimize the discrepancy between what you want to learn, the target equation, and also a auxiliary function known as the variational distribution Q, right, which is very oftentimes known as the vehicle to achieve approximate learning. And then thirdly is a uncertainty term, which governs the compactness of the model that you learned. It turns out that if you plug in different instantiations of the experience of the way of measuring divergence and the way of measuring uncertainty, you can actually recover many, if not most, or even all of the known learning paradigms that we use in machine learning and AI. And here is just a little kind of a summary of a tree like generalization of this equation to all the learning paradigms. And here we have a table showing you how the instantiation look like when you want to generalize. So just to walk into a few examples so that you can see how convenient it can be. For example, if we plug in the data experience into the standard equation and using a indicator function to indicate the presence and the absence of the data points, then you can actually reduce the standard equation into a form that is identical to what we see in the maximum likelihood learning with or without label. You can go further by replacing the experience term in the standard equation with not a plain data experience, but with a oracle data experience, meaning that you introduce a function u of x, which can measure the informativeness of the instance x, and then using this equation to formulate the oracle experience together with the data experience, then plug back into the standard equation, and then optimize the resultant function. You will arrive at a iterative algorithm which look identical to the active learning algorithm derived in this paper. You can go further and plug in a reward experience. As we know that in reinforcement learning, our goal is to learn a policy, which is the conditional distribution of the action given the states. This is a little bit different from the maximum likelihood learning. And also you begin with maybe also a state distribution mu. And now we can plug in, the reward function, under a certain given, environment and action. And also to introduce both the state distribution and also the policy distribution into our formulation of the auxiliary Q function, and then plug them back into the standard model, you actually will arrive at a optimization algorithm which really look identical to the RLS inference algorithm introduced by Diane and others. In fact, if you want to take a different form of the reward, such as a exponentiated form of the reward, then you can actually also derive a policy gradient algorithm using these standard models. So without going further, you can also try, replacing not just the experience function, but also the divergence function with some other forms. And then you recover, what is known as the adversary, generative adversary learning paradigm. For example, you can replace the D function with a Jensen-Shannon divergence. Previously, we only use cross entropy. Here, you use a JS divergence, and you plug in the experience, with a binary classifier. Then actually you can recover, a vanilla GAN model. And if you want to try other experience and try other divergence function, you will have a more advanced form of the GAN model. So this is just how it looks like. For example, introducing the Jensen-Shannon divergence into the equation. You can actually, solve it, using a very standard EM approach, of which in the M step, you are going to minimize what is known as the inference function, of that standard model. And the inference function is obtained by solving a convex dual, of the original loss function. And in this convex dual, you actually are having the chance to parameterize a conjugate function using, for example, a whole, form of a neural network to be a classifier. And then once you plug them back into the equation, you resulted in a minimax, formulation where you simultaneously learn both the generative model and also the distributive model. So what's the big deal? Why such a standard model can be interesting? Is there any value other than just summarizing all the formula into one equation? Well, here I suggested a few practical utilities of this practice, which namely results in learning from different experiences altogether, and also allowing complex interactions between experiences. And also there could be a better paradigm to do theoretical analysis and also to implement multi-agent learning, where each agent can use their own standard model to integrate multiple intrinsic and extrinsic experiences. So I will say a few words about each of these examples. So learning with all experience, as I said, is a very intrinsic needs, in complex tasks, where human beings have our brain equipped with a mechanism to really integrate from all experiences. And in here, I give two instances about the different style of multi-experience learning. The first one is to reuse and repurpose originally specialized algorithms. So as we know, in machine learning, one of the reason, for example, every year we see so many thousands of new papers published is because people are pushing very hard to develop highly specialized algorithm for every specific model and very specific problems. But there has been less effort to ask whether the algorithm can generalize to different application scenarios. And here, I argue that with the standard equation, this can be very easy. Okay, for example, let's look at a algorithm of Costil regularization, where you want to regularize the model with some additional rules, such as constraints or boundaries. Right? But what if you have many rules and you want to actually also learn the importance of each rule? There isn't really an algorithm, designed in the scope of Costil regularization for that. But in reinforcement learning, there are plenty of algorithms allowing people to learn, the parameterized rewards, both extrinsic and extrinsic. Right? And argue that this type of reinforcement algorithm can be actually introduced into the Costil regularization paradigm to learn the rules. And here is how it's done. Because reinforcements, rewards, and rules in Costil regularization can be all encapsulated by the experience function under the standard equation, right? And we know that, in reinforcement learning, we have an algorithm known as the max-end reinforcement RL, which allows you to learn the parameters of a parameterized rewards. Now, we actually can parameterize our rules to be learnable using the same kind of formulation. And then we can just plug in this max-end inverse reinforcement learning to learn now the weights of the rules. So without inventing a new algorithm. Likewise, what if under the supervised learning scenario, not only we just passively take data examples, but also we want to start assessing the utility of every data example in terms of their informativeness. Same thing, you can make formulate a learnable data augmentation function for each of the data examples, and then treat them as a new instantiation of the experience function and plug them back into the standard model. And then from the arsenal of, from the, the library of reinforcement learning, we have an algorithm called intrinsic reward learning, which actually breaks down, every, reinforcement learning, instance to be, a combination of both the extrinsic rewards coming from the environment and also the intrinsic experience associated with each of the action state pairs. And these action state pairs can correspond to, just the training examples, in our maximum likelihood scenario. And then the same algorithm now can apply to the, active learning scenario to start to learn the weights of every example without reinventing a new algorithm. So likewise, you can imagine many of the techniques developed in certain areas, as just mentioned, reinforcement learning, but also variational inference and all that, which are used to achieve better results. For example, in reinforcement learning, we have techniques such as a proximal policy gradient to enhance the stability of the training of policy. And also in variational inference, we have an important sampling technique to also boost the stability. And we know that stability is not only needed in reinforcement learning for policy learning, but also it's very much needed in gun training, because the gun models are notorious for their instability during training. Right? So again, they are all instantiations under the same standard equation framework. Therefore, all these tricks in PPO and in important sampling can be applied to learn the adversarial networks. Right. So here are some results showing you how these previously specialized algorithms help to learn and will help to specialize the gun model training by scoping the magnitude of the updates, or by controlling the fluctuation of the descriptive loss and the generative loss and so forth. So another benefit outside of learning with all experiences is the potential of developing more general algorithms, as a turnkey solution simultaneously to multiple solutions. In fact, here I have a few more examples of known as experience integrations. What if you have multiple experiences coming together? And we also know that in training language models or in training NLP and the vision tasks, very often we want to achieve some compounded goals, such as in controllable text generation. Not only we want to generate linguistically correct text, but also maybe together with a certain type of sentiment and with certain type of linguistic rules, right? So you can now train such a model with experiences coming from sentiment classifier, linguistic rules, and the language model, smoothness, to train them together to produce a more controllable text generator. In another function application we worked on, just as a toy problem, what if you want to develop a virtual try-on algorithm that the shopper, the consumer, can actually post in front of the camera and get experience of having different dresses on their body. This is actually a pretty difficult generative model, because for all the gestures presented by the consumer, there may be not enough examples to train the model. Therefore, we can combine multiple training experiences like the following, right? You can, for example, begin with a large amount of data of a standard posture, and then you can introduce small data with specific kind of gestures with different dresses on, but they are very small, maybe even none in terms of the amount of data size. But you can also incorporate the human gesture constraints, so that these constraints can regulate how the output configuration can behave in terms of the body gestures, the positioning of the different body parts, and so forth. And with that, you can actually arrive at a pretty robust image generator, even with very small supervised experiences. So here is a demo. You have the source, and you start to put the different gestures on for the same dress, and here are the different body posts that can be used as constraints. You can see that the basic model with no constraints generates a very low quality images. Once you put the body pose as a hard constraint, you get a slightly better kind of picture. But because there are hard constraints, they do not allow a flexible interplay between the training images and the constraints. But if you have a learnable experience, so that you can have a different weights of the importance of different gesture, you get better and better image quality. Right? So this is again another kind of utility of the standard model, which allows you to train a model with multiple heterogeneous type of experiences. People may ask, is there a way to develop a turnkey algorithm which can be used to simultaneously solve multiple learning paradigms? Obviously, this is possible under the standard equation because now all the different learning paradigms are summarized using a single set of equations. And here is basically a very straightforward display of a EM style algorithm, the alternating projection algorithm directly applied to this equation. And you can see already this form is a generalization of a number of known algorithms that we use in different learning paradigms. There is a step where you update the variational auxiliary model in which the previous form of the current model to be learned is integrating with the new experience coming to training paradigm. Right? So you can call them also as a teacher step or maybe an E step, in the conventional learning paradigm. And then in the second step, you are going to optimize the parameters of the target function you want to learn. And this can be also understood as a student step or a maximization step in the EM algorithm. Right? So this particular generic alternating optimization framework can be further specialized with a lot of tricks, such as the PPO trick I just mentioned, and also many of the other stabilization methods we used in GAN and other frameworks. There exists even more advanced technique to further augment this framework, but still without losing generalizability. For example, we can imagine solving the standard equation in its dual form, which result in a very interesting formulation that you see nonlinear interactions between different experiences and different features. So this phenomenon was originally discovered in traditional paradigms such as a support vector machine and such as structured maximum entropy distributive learning. But in here, they can actually also be leveraged over all the learning frameworks that can be summarized under the standard model. And actually, that's a very interesting opportunity because now your reinforcement reward experience, your rule-based experience and data experiences can interact not only in additive fashion, but also in quadratic fashion, where a kernel trick can be introduced to incorporate higher order nonlinear effects. So this kind of directions hasn't been explored yet, but we are actually actively looking into such potential opportunities. So I won't go on with more instances of generalizing the learning paradigm, but I do want to mention maybe another opportunity that we are also exploring, which is performing some more general and a universal theoretical analysis of learning paradigms. So here is one instance. Right, there has been a great enthusiasm these days of understanding the adversarial robustness of learning algorithms, but in a very limited scenario, especially in, for example, image classification and so forth. And here is a demonstration of such an image classification problem. For example, people may ask, where Eric Xing right now, is working, after he took on, a leave from Carnegie Mellon. Well, I'm actually now working in a new university, right? But if you present this problem to an image classifier with the information of the input being corrupted, by some kind of engineered noises, you may be able to deceive that classifier, to believe in, a different type of outcomes. Right? So this is what is known as the adversarial robustness, of classifiers. And the reason behind such a vulnerability is because different classifiers, may have a different sensitivity to boundary risks. such as I show here, between, a standard cross entropy minimizing, logistic function versus a margin minimizing SVM framework. Right? And in higher dimensional model, you actually have similar phenomena. So there is a need to start exploring maybe a integration or maybe a balance trade-off between different type of risk. So here we define, in an early piece of work, what is known as the natural risk, which just described, the probability of making an error, right, over the entire distribution of the data. But also you can define a robustness risk, which only cares about the mistake you made over data points under, a small regime near the boundary. And there are classifiers which can be positioned very specially to optimize each of the risks. For example, in this piecewise constant classifier, you can show that a Bayesian optimization optimal classifier can be optimal in terms of a natural risk, but the worst in terms of robustness risk. But for a trivial classifier, like an all-one classifier, they actually achieve a pretty good balance. So that means, there is a opportunity and even a need to design a type of new loss function, that provides you a natural integration or trade-off between different types of risk function. And in a paper we published a while ago called Traits, we show that you can actually bound the difference between the robustness risk and the natural risk, by introducing a alternative term that is, modeling, the interaction of, samples, within the boundary and also, in away from the boundary, and to see, how these two type of risks interplay each other. And that leads to, a new surrogate loss function where you are simultaneously minimizing both the natural loss and also a interacting term that consumes the boundary loss. Right? So this particular analysis leads to a pretty good collection of solutions, that allow us to win, a neural-based competition of adversarial challenges. But our technique developed then was only applying to, a very small family of, discriminative models, which only, were trained on data experiences. With the standard model, we could easily ask, can we plug in the F function with this more general form so that you can define, a adversarial robust algorithm over not just supervised learning, but also, Bayesian optimization, active learning or reinforcement learning. Right? So these are opportunities I see to be very exciting. Okay, so now that I presented, a unified and hopefully more generalizable approach to learning based on standard model, let's look a little bit deeper to see how to do meta learning, which is to really concern a problem of learning to learn. Why this problem is interesting? Because for any learning paradigm, including the standard equation, you not only need to learn the model, but also you have many free knobs, which are known as the hyperparameters or model architectures that could also impact the outcome of learning. Right? For example, the problem of hyperparameter optimization concerns about how to choose the best configuration of those hyperparameters that can result in faster convergence, of the learning algorithm, or maybe even stronger results of the learning loss. You can also, in fact, another problem is concerning neural active search, especially in the domain of deep learning. What is the best topology or architecture of a deep learning model that can give you best results? In fact, if you are savvy into system, there is also a space, in the back-end system configuration, how to parallelize, your work, into a cluster, how to schedule multiple jobs. So these are all, problems in the meta space that can indirectly influence the learning outcome. So learning to learn is the problem concerning how to, improve this type of meta learning, with respect to either an intrinsic loss, such as the quality of the model, or a extrinsic loss, such as the energy consumption or other extrinsic issues people want to optimize against. And one of the major goals, under the umbrella of AutoML is to really introducing automatable, approaches to do this type of tuning, because they are obviously very labor intensive and domain knowledge intensive. Right? But this problem itself is very different from what I presented earlier in the standard learning, where you have a explicit form that you can optimize from. By definition, the problem of tuning in the meta space is oftentimes concerning a black box, which is the entire training algorithm or the training procedure itself. You cannot differentiate, a explicit function to find the best configuration. All you can do is to give it a query, try to train the model under a specified parameter, hyperparameter configuration, or a given neural architecture, or a given system configuration, and see how the result looks like, how fast it is, and how good the outcome is, and then give it another try under a different configuration. Okay. So this is a typical scenario known as the black box optimization. So we ask, can we even tune automatically, maybe even based on a model-based approach in this paradigm? Well, this work has been actually studied in a number of other scenarios, in, for example, optimizing laboratory equipments, material discovery, and so forth. And the approach is the following, right? You want to find a domain, which is the space of hyperparameters, for example, or the space of all neural architectures and so forth. And then you want to, best optimize a objective and with the least cost. And the most obvious method is to basically bring structures into the search domain, such as, a grid search or a random search, so that you can pick configurations and then try it on the black box, which is obviously very expensive and not very scalable to very high dimension, because if you have too many hyperparameters, or you have the entire space of all graphs of a neural architecture, this type of grid or random search is simply unaffordable. So what we are going to talk about is a model-based Bayesian optimization approach, which hopefully can be more efficient and automatable. So here is the setup. Under a Bayesian optimization, the main idea is to use a probabilistic acquisition model to, intelligently plan the queries and hopefully perform, efficient optimization. So what is a probabilistic acquisition model? Well, it is a model that maps each configuration of the hyperparameters, for example, to, a uncertainty over the objective, such as the validation accuracy and so forth. Right. So this graph basically shows you, a Bayesian view of this optimization, where, each curve is a estimated probabilistic acquisition model, and then all these curves demonstrates you the uncertainty over such a functional space. And then we're going to also need to introduce what is known as the acquisition function, which defines the utility, okay, of different configurations, capturing both the quality of the output and also the uncertainty of the output, so that you can accordingly decide where to probe next. Right. So the problem formulation is a nested optimization problem. In the outer loop, we are going to keep learning and improving the probabilistic acquisition model to better capture the uncertainty, of the input-output mapping. And then in the inner loop, we are going to further optimize the acquisition function to, enhance its ability to capture the utility, of the trial of the query. So we can actually step into this algorithm and look at what each step is taking place. For example, we assume that we already have a couple of instances of query and outcome pairs, call them X and Y. And we can also assume that we have a prior distribution, of the probabilistic acquisition model, such as a Gaussian process. And then given the prior and given these few instances, you can come up with a posterior distribution of the acquisition functions or acquisition model like this, right? And then based on this, you can now define a acquisition model which captures the utility of the outputs in terms of the value of the output of the the accuracy, for example, and also the uncertainty. That's why you see this very interesting shape that in a place where the output has a high value, it seems to be high, but also in other regions, even if the output value is very low, but if the uncertainty is very high, then you can still have a high utility in this particular query position. Yeah. And then this one can be used to pick where the next query should be taken. And then you apply this query, to the black box, you get an output of, the intrinsic rewards or value. And then you get now a new pair of data points of X and Y. You can now further kind of update the probabilistic acquisition model. So that's kind of the bigger picture of our black box meta learning framework based on a Bayesian optimization. Maybe an interesting thing to mention on top of this is how to pick the acquisition model. So this one is actually obviously a very mysterious function because it is impacting both the quality of the probabilistic acquisition function model and also the speed and the efficiency of the learning. So here I just share with you some intuitive ideas about how to define the acquisition function. Right. So it is to capture both the utility and also the uncertainty of the query. And imagine that under a Bayesian optimization framework, we have a posterior distribution of the utility function, right? And in picking the next query, you can actually sample a few such functions of the probabilistic acquisition model. And each of them will give you an optimal prediction of where to try next. And as a result, you actually have a posterior distribution of the optimum trial points. And you can imagine that the best point to try for our next query could be chosen based on a information theoretic principle measured by this, right? This is a measure of the uncertainty, of the current set of query and the outcome pair. And adding to one more query and the outcome pair, you can imagine that if they are wisely chosen, they could reduce the amount of uncertainty of the entire query and the mapping distribution. Therefore, we can use the expected information gain as a function of the acquisition function, so that we can pick the next trial points. Right. So this is just the one instance of parameterizing our acquisition functions. So as a result, we come up with a mechanism that is again very generalizable, for all different types of learning paradigms, using the same optimization black box, a Bayesian optimization driver as a meta learning mechanism. And you can see that across different problems, such as random forest regression, gradient boost regression, and in fact here we have also neural networks where you can see more and more number of hyperparameters. The mechanism that I introduced based on Bayesian optimization for black box optimization, it seems to be consistently outperform many of the other heuristics based on random search or based on genetic algorithms and so forth. And this same technique can be used beyond hyperparameter optimization. In fact, you can also use the same technique for neural architecture search. And here the trick, of course, is to map the graph of a neural architecture into a more searchable space, and also more amenable for posterior Bayesian optimization. And one of the techniques we use is to use a so-called optimal transport to define distances between neural architectures. so that you can have a pairwise distance matrix of all the instance pairs, and that naturally allows us to using a Gaussian process to define a posterior distribution of the functional distribution of the probabilistic acquisition model, right? And then you can actually also introduce another Bayesian network to be the probabilistic acquisition model itself, to give you ways of modeling a network through a network, and allow neural architectures to be systematically experimented and tried. We can actually also use the same technique for system level optimization, as long as you are willing to use a model-based approach. And in this case, for example, we can introduce a model called the good put that simultaneously model both the reward resultant from tuning different batch size, which result in changing level of throughput, or different level of learning rates, which leads to different level of efficiency. And then based on a Bayesian operation framework, you can optimize the good put using hyperparameter search type of technique. And we actually come up with another system called AdaptDL, which can actually achieve this type of optimization problems automatically. So with that, I'm ready to close by maybe mention a few words about the tooling, because all the technique I just introduced, could still lead to very complicated implementation, depending on who implement that and on what kind of particular problem instances you implement. You can still result in very complicated system and implementational challenges, which is still not scalable. But from what we presented so far, we can probably recognize that many of the machine learning tools that we use in terms of different algorithms, different loss functions, and different architectures, can be systematically collected and categorized, just like what we do in our Lego games. They have different parts, and they actually can be assembled using the kind of Lego assemblage concept. So I call them the machine learning Legos. And in a toolbox, which we call Texa, we actually come up with a interface that allow the users to pick and choose different model components, such as different decoders and encoders, different loss functions, different instantiation of the experiences from data rewards and other type of responses, and also different optimization algorithms that is implemented in a standardized way to achieve a compositionizable solution to your variety of different modeling tasks. And then together with that, we introduced another tool called Forte that builds on a universal data representation, which we call data pack, that allow you to encapsulate all different experiences, such as different modality of the data, different rules, using again, a standardized ontology that can capture, different instantiations with the same format, and then, translate them between different, building blocks of a pipeline. And in that way, you can build, multi-component, solution of a real kind of a machine learning problem, such as a report generator, which involves both, vision and NLP task, and a whole collection of different subtasks in training and inferences, using, a more, again, a Lego style assemblage technique. Further down into the meta learning, we also have a toolbox called Tune, which allow you to accommodate different types of input models and the search domains, and using a encapsulated, probable, suite, to do different kinds of, Bayesian optimization, leveraging on different choices of acquisition functions and acquisition models and so forth, and also output different types of, extrinsic and intrinsic outputs. So last but not least, what about deployments and the large-scale implementations? Here, this is beyond the scope of today's talk. So I want to just mention a few words about the type of work we did in the past, so that we actually can at least bring them together under the single umbrella of Lego learning, because they, again, do not require, in-depth wrangling and massage once they are implemented. So suppose that we are given, a computing graph resultant from, a complex model, and also, say a cluster of machines. In fact, building a distributed strategy involves making choices of partitioning, placement of jobs, synchronization strategies, and scheduling, and so forth, right? So this very old-fashioned problem of distributed strategy can be actually, systemized. So here, we can build a compiler over different, variety of distributed machine learning strategies using, again, a model-based approaches, which is defined on data, resource, and the different choices of strategy. And we come up with a algorithm known as the AutoDist algorithm, which actually can even outperform, human-designed distributed strategies, as shown in this graph. And this tool is called, AutoDist, which actually builds on, again, the Lego of different system components for communication, for consistency, for encoding and decoding of the training and communication signals and scheduling and so forth. And last but not least, when you have a team of workers working on multiple training tasks on the same computer, you also can replace the work of the system admin, again, with a co-adaptive scheduling algorithm, which optimize automatically this good put loss function, as I just mentioned, over the space of throughput and statistical efficiency, to achieve best resource allocation, and also a hyperparameter optimization over the throughput and the learning rates and other system level configurations. And again, the results can be several times better than a manual task, even by a human expert who actually knows the detailed nuances of both the machine learning algorithm and also the system configurations. So with that, I want to conclude by summarizing that even though a machine learning task in real world can be very complex and involve many levels of optimization, there is an opportunity to build models at all these different levels to make the results and the efforts more predictable in terms of the amount of work needed and the quality of the outcome resulting from the work. And what I showed just now was just a collection of results that we developed over the past few years in each of these dimensions using a more or less model-based approach. So in a sense, there is a unifying mathematical framework and the philosophy behind all this work, even though they use slightly different techniques and tricks. All the tools I just mentioned is public available in this GitHub repository called Castle. And some of the work was actually quite well recognized recently with best papers at ACL, at OSDI. But we are also working very heavily on integrating our tools with existing paradigms such as the PyTorch, the Microsoft MI, Ray, and Hugging Face, and so forth, so that people can really take advantage of our open source tool with existing good solutions in other domains. So with that, I want to conclude. I see machine learning really having a need to going toward more principled and more Lego style learning through composability, automation, and scalability. And hopefully at some point of the time in the future, we don't have to do this type of machine learning, but to do a more systematic, predictable and cleaner effort to complete even complex tasks, such as the ones worked within Baidu, for very real world applications. Okay, so with that, I want to conclude, and I'm happy to take some questions from the audience.
Thank you very much. I see that there's quite a bit of interest in the last part, the parallel computing, the distributed computing part. People just said they didn't quite get what's the novel part of the contributions. I'm sure there's a lot of things, but you went over the slides really quickly.
Yeah. That's I meant to be giving a more kind of method talk and not a system one, but I can say a few words here, or I can make another talk in the future, for the system only. There was a tutorial, in fact, on my website that we give at the KDD early this year, which presents a very comprehensive overview of co-adaptive and the systematic optimization in the system space. The novelty here, if I were trying to summarize, one is maybe the systematic formulation of distributed machine learning in the space of partitioning the job of bigger model and big data into model parallel, data parallel, and pipelining parallel kind of a system configuration. Making choices of different communication strategies, such as synchronous, asynchronous, or partially synchronous framework, and then prove theoretical results of their consistency and correctness. And thirdly, building system topologies to give you adaptive and generalizable wiring of the nodes or the GPU cores in your distributed framework. Do you go with master slave? Do you go with ring? Do you go with peer-to-peer? Depending on the policy you use, such as a parameter server, such as reduce, or maybe even other combinations of technology. In fact, one of the novel contribution we had in our work is that with such a very fine granular definition of all the options in the SysML framework, we can now compose heterogeneous strategies even within the model, that different parts of a larger model can leverage on a slightly different local strategy for distributed machine learning and training. And then another novelty reflected in our recent OSDI paper of AdaptDL is that you can achieve both high throughput and high statistical efficiency by combining the predictive model defined on both configurations into a unified framework, and then you optimize in the space of system scheduling and also job partitioning as a function of the throughput in terms of batch size and also the learning rates for statistical efficiency. Right. So I think this is just a very high-level summary of the novelty, but if you're interested, our 3-hour tutorial at KDD gives a pretty comprehensive review of all these techniques that I just talked about.
Very good, thank you. There's a question in the chat box, but before that, I wonder if you may be related to the question I have. So how's, or what do you think about the pathway that Jeff Dean just mentioned? How's that related to your system?
The pathway.
Yeah.
In a sense, it kind of goes back to what I mentioned at the beginning about some of the machine learning trends. If you look into pathway, I believe it is a very classical idea based on mixture of experts. It's a technique that has been, of course, practiced and innovated, over the past decade by many people. But I think Google is trying to add some fresh initiatives into this overall umbrella by, for example, building component models under a mix of experts to be bigger to be more heterogeneous and also to involve maybe certain system components to make it auto-tunable and also scalably trainable. So that's how I read pathway, but fundamentally, I think it is a new name for a very well-developed collection of fundamental techniques that is already there, with of course a more unified, production-oriented framework toward its maybe productization and industrialization. In fact, I think a mixture of expert is a very, very interesting and promising direction, because it's having the potential of allowing people to achieve actually what I also mentioned just now under standard model, just by having a umbrella kind of integrator, over heterogeneous collections of all different models. Right now, I think it is about a mixture of experts, of different experts with toward the same task maybe, but using different model configuration. But it could also be that the mixed experts each are doing a different task, and especially in the multimodal domain. And then you can somehow integrate them using a shared representation, for example, for both visual and lingual and maybe even logical concepts, to achieve a mixation of experts in a meta space in a more efficient way.
Thank you. There are quite many questions in the chat box. Maybe can you go through them?
Oh, okay. Let me. Let me open the chat box. Okay, let me read. It seems that the ML Legos are only for single task. That is, we must do search and the Bayesian optimization for best composition under specific task. Is it possible such as a setting could enhance the task generalizing problems? If I understand this correct, problem is that, are you asking whether our meta learning or Bayesian optimization can go beyond just tuning one task, but a concatenation or a pipeline of multiple models? If that's a problem, the answer is yes. Yes, actually, we are in the process of deploying the tune algorithm, the Bayesian optimization algorithm, over not just model, but a pipeline of models. Technically, it's not really, a dramatic difference, over what we are doing now under the same model, because same model, if we are treating them as a black box, then all we see is a set of hyperparameters, or structures that we need to search, in the configuration space. We don't actually care what is inside the black box. So in a sense, the whole pipeline is a black box, right? But of course, in the implementation side, it is challenging, because that means they have to be already integrated smoothly inside the black box, so that multiple tasks can share the same data architecture, and also can share, kind of a workflow, in terms of the input and output between different components, so that when you tune parameters, you trigger a cascading effect inside, the pipeline. So we are actually, using the Forte framework I just showed, to be the vehicle for such a pipelining, and hopefully, in the next couple of months, we're going to release, a new version of the Forte, which integrates, the meta learning framework from Tune into that. So if that's what you're asking. No, I'm not sure whether I'm answering question, but let me just read through the next question. To trade off between robustness and accuracy, your paper mentioned that high frequency component and low frequency component are key to this issue. could you please give an example of both high frequency? Okay, that's a different paper that I didn't even mention here. Thank you for your interest in our papers. High frequency and low frequency. In fact, this is a very domain-specific problem, and it depends. For the current computer vision applications, we found those high-frequency signal to be mostly corresponding to the less semantically savvy, but more kind of a generic signals, such as the background, in a natural image, and so forth, which are kind of high granular but less variable. Then the low frequency components correspond to those semantically more sensitive foreground information, in our image. So that's what we see empirically so far. And you can imagine once we have that kind of a breakdown, you can just cut off the high frequency and save the low frequency and preserve the semantic information. But actually, the real issue in application is actually not that simple. Even in computer vision, semantic is a very subjective term, because what if I happen to be very interested in the background, not the foreground, right? For example, I'm not interested in what is sitting in front of a beach scene, but I'm interested in the beach or non-beach itself. Then suddenly the configuration of the semantic switched. Then suddenly the high frequency information may be more relevant. So I don't actually have an answer, to definitively map high frequency and low frequency, into what a person is actually interested in. But I can see that they, can be separated. In natural language, input, we actually have less of a understanding about high frequency and low frequency, because the encoding is not through a convolution neural network, right? They have other type of recursive or LSTM type of framework or transformer input, into the latent domain, where the signature of the feature is not characterized by their frequency in terms of the Fourier transformation terminology. So we are not yet, fully understanding, what could be the characteristic of the robust signal or the part of the unrobust one. So that part is still open. The next question, I have a similar question. Is it possible to use Bayesian optimization for general linear programming problems with binary variables? I'm not clear what exactly is the configuration here, but I just want to reiterate that our Bayesian optimization is for black box optimization. So we actually don't care what is inside a black box, as long as you can inject a hyperparameter and run that algorithm and come up with a intrinsic value output, such as the accuracy of regression, or the accuracy of the classification, or even how much energy you spent, right? So in principle, the Bayesian optimization is very generic in terms of where it can be deployed. So the real question relevant to your problem is that what's the interface? How your general linear programming problem, is offering a window for being optimized. Are you optimizing over any hyperparameters inside the linear programming? I actually don't know what is your hyperparameter in the linear program. Or it is your hardware configuration, how many machines that you want to do, and how to distribute your larger linear programs, such as a big matrix, into different parts. So then the hyperparameters becomes, the number of machines, the communication strategy, such as a degree of asynchrony between different machines. Then, obviously, this can be optimized through a Bayesian optimization approach.
Huang, does this answer your question?
Sure, please.
Hello, can you hear me?
Mm-hmm.
Hello, can you hear me? Oh, yes, thanks for your talk. Yeah, so I think it's some kind. So maybe my question is that for like hyperparameter optimization, for example, neural architecture search. So this kind of problem can be like written as a discrete optimization problem. So it can be maybe written as like a binary, optimization problem with like binary variables. So my question is that can we like go one step further, like for general like linear programming solver, general linear programming problems with like 0 and 1 variables? Is it? Yeah, so maybe my question is, are there any people trying to use like Bayesian optimization, like for solving general linear programming with like binary variables? And is it possible, or is it like a good direction to explore?
Interesting question. So I think it's solving a different problem here, right? So the Bayesian optimization, at least in this presentation, is focusing on, finding a configuration, in the hyperparameter space. It could be in a discrete hyperparameter space, to achieve, the primary goal of configuration in that space, to be dictating the efficiency of the training task. Now, what I'm not clear is that your discrete optimization is the primary problem or the meta problem, right? If it is in the primary problem, I'm not sure, what is your free knob that you want to use in solving the problem better, because here I'm positioning them to be learning to learn. It is not to learn, it's to learn, in the sense that you already have a solver for your linear programming or for your discrete optimization, and you want to solve it even better using your existing mechanism. And then my Bayesian optimization is deployed here, because it is giving you a very efficient generic kind of a search mechanism, in the configuration space, and also in the way of measuring the uncertainty, over the configuration you use to solve your primary problem. I think your question was a little bit vague in terms of whether your linear program problem is the primary or the secondary problem.
Yeah, I feel like, yeah, the general linear programming problem with binary variable, yes, seems to be a little bit different from the like general like hyperparameter optimization. Yeah, I think maybe there are some like difference. Yeah, and maybe this difference makes it maybe cannot directly use Bayesian optimization. Yeah, that's my current feeling. Yeah. So yeah, thanks for your answer anyway. Yeah, thanks.
Okay, thanks. There is another problem raised in the chat. Let's see. Your idea of unifying ML models into a standard equation is quite interesting and innovative. Thank you. My ML looks that more diverse and noisy compared with physics. Further, ML is in fact more data-driven. That is practically why right now researchers and engineers like those from OpenAI and more are more interested in building pre-trained models, targeting at resolving downstream tasks in a few short fashion. This seems to be more close to how humans resolve problems. How do you feel about this trend? Yes, I think your question is more of a comment rather than a question. But in terms of the trend, yeah, I think pre-trained model, in my opinion, is a kind of experience that you can also incorporate. It could be either a way to instantiate the parameters of the model that you continue to optimize, or it could be treated as a pure add-on experience if your subsequent model is additively combined with the previous models. So I see them to be maybe possibly leveraging on the standard equation for the integration, but I don't have a very strong opinion about how to how should I say commenting on this trend, whether we always want to be relying on very pre-trained models. My hunch is that yes, the pre-trained models, if they are pre-trained already, are not supposed to be always retrained because they provide background knowledge. So it doesn't change our subsequent learning scope of building appropriate models for what we call the few-shot learning or one-shot learning, in a model-based fashion. So in a sense, all the learning paradigms, including the standard equation described, can be plugged into the subsequent, small sample, and pre-trained kind of framework that you just mentioned. I don't have time to, I'm not in a position right now to incorporate maybe or discuss a new kind of project that we are working on, which is a new look of, how should I say, divide and conquer, larger pre-trained models to really see them as a single one piece of all parameters being pre-trained, or kind of zooming into sub-models in the pre-trained model and only utilize that part for subsequent training. So there are some ongoing work we are working on using some kind of a mean field and variational inference framework, but it's very, very premature, so I'm not in a position to discuss that now, but maybe in a few months, we will have some new results to share.
There's one more question. I hope we have time.
I'm curious about your thoughts on how and whether Lego style learning or modularized models could help with neural nets generalization and catastrophic forgetting. Not sure. I understand this question very well. So I'm talking about Lego learning at different levels, right? So one is in the machine learning ops level, that all the building blocks, could be Legoized and pre-made and then plugged in. What you seem to be talking about seems to be peeping into the model itself, that a larger model could also be assembled or composed, from, for example, layers and sub-networks, or even different choices of activation functions and so forth. If that's the case, I don't think we covered this type of design space here. We are leveraging on the existing design space, but people are already composing, neural network in this way. For example, the big transformer, the big, language models was actually built off, smaller transformers of all kinds. So there is already this. The forgetting and the compositionality part, forgetting and the catastrophic forgetting part is, yeah, I'm not very familiar with that. I think it's, yeah, it's not what I plan discussing here. I would say it's more in the space of the capacity, of larger models, being unmet by the smallish of the training data. Therefore, what we mean by catastrophic forgetting, I'm guessing that they actually didn't even remember or have the kind of the buffer, have the opportunity to be remembering, some kind of signals from the data if the model was made too large and the training data was not large enough. Again, that's just a wild guess. I don't actually know for sure why that is happening. Wow. I keep getting one more question. Let's see. Maybe I will sample one more. Some ML problems have thousands or even millions of training samples, yes. But many other ML problems have a very small training data sets, etc., less than 100 training samples. How could the ML platform help ML problems with a very small or few training samples? What if there are not enough similar tasks, in terms of meta learning? Yeah, that's a very good question. I think, if you look at some of the examples I gave, for panoramic learning or learning from all experiences under SE, is to address, some of the data scarcity problems. Right? I guess, with small training examples, the only paradigm of the learning that is impacted or hurt is the so-called supervised, or unsupervised maximum likelihood-based learning, because they are very data-driven. Right? But if you look into Bayesian optimization, and if you look at, for example, active learning, or even regularized, optimization, these are places where additional information such as rules, such as prior knowledges, and also data weighting can be brought in, right? So the difficulty, in the past is that all these different techniques to address, a small data problem isn't coming together naturally, or can be deployed or integrated naturally. I think the standard equation is at least offering a, a unified mathematical framework for you to practice all these panoramic experiences without switching paradigms and without using different equations. So to some degree, it is solving, the data scarcity problem. If you don't have enough data for supervision, you bring in knowledge graphs, you bring in rules, you bring in prior knowledges, and so forth. Okay, so that's something I would recommend. In terms of meta learning, I want to reiterate that the current meta learning that I was talking about is really treating the learning task itself as a black box. So we are not basically, taking into account yet what is inside a black box. So in a sense, we are not kind of, hurt by any risk, inside that black box, but also we're not taking advantage of any opportunities inside the black box yet.
Great, thank you. So I already promised Professor Xing that I will let him go after 90 minutes. So time is up.
Oh, okay. It's very
thank you so much.
Yeah.
Yeah, so please do come back in a few months, as you mentioned several times. So a lot of people are very eager to hear your new progress and the new deployments, which will come soon. So this is very exciting, and thank you very much, Professor Xing. And yeah, so I hope you will get some break and get some rest after the talk.
I'm going to go to work now. it's
okay.
Thank you very much. Great to talk to you guys.
Okay, thank you.
Sure.
Yeah.
Bye-bye.